So we are going to do errors in hypothesis testing, but before that, you should know what a hypothesis test is. It is a test for some parameter. I want you to go back and look at 2023, but we will talk about parameters later on. But to do this topic, all we need to know is the null and the alternative. And in a statistical sense, null means no effect. The alternative would simply mean there is some sort of an effect, or there is some true effect. True effect that is significant. So you have null, you have the alternative, and the alternative is the opposite of the null. But okay. Get to go to a TV show and participate to win $1 million or $10 million. You get one chance to guess the animal behind the door. It's either a monkey or it's not a monkey. So I'm going to call monkey to be H0, not a monkey to be H1. Later on, we will talk about, as you know, a specific case involving statistics with a parameter. But for now, to understand the types of error, I'll just call H0 to be monkey and H1 to be not monkey. So Jamie and Jessie are a couple, and Jessie claims to be a psychic. So they try this game 100 times at home. And the plan is to send Jessie to the game, and Jessie is going to win us $10 million, or win Jamie and Jessie $10 million. And this is what happened in the 100 trials that they tried at home. What's the key? Or this, Jessie's guess. Good. Let's see, 100 trials. So let me just put this in here. Well, no, let's see. Let's see. 20. So 100 trials, and these are the outcomes that Jessie has. Let's say if Jessie can win us $10 million, win them. So do you think that Jessie can pull it off? Well, they have a smile. No, it's not going to happen. We will see why. So monkey, she was able to guess only 30 out of those 100 times. She made a mistake here because behind the door there is a different animal. She guesses it as a monkey. And over here, behind the door, we have a monkey, and she guesses it as not a monkey. And over here, only 10 times, you have some of the animal behind the door, and she guesses the exact same thing. So based on this, this is not going to be good for them because they're not going to win money in this case. So how do we relate this to statistical tests? So H0, H1, H0, H1. Yes. So when we move to H1, the terminology is simply rejecting H0. Do we agree? Yes. When we're saying not a monkey, we're going against H0. So you're rejecting H0. So that's H1. Same over here. You are rejecting H0. Good. So did Jesse make a mistake here? No. So no error. Did Jesse make a mistake there? Yes. Right? 40 times. How about here? Yes. How about that? No error. Good. So in this case, the null is true. In other words, the monkey is behind the door. But Jesse ends up concluding that we need to reject the null. In other words, it says it's not a monkey. So this is what we call a type 1 error. And the notation for a type 1 error is alpha. Naturally, if you have to take a guess, what would you guess that error to be? Beta type 2 error. So you are rejecting the null when the null is actually the truth. Monkey is what's behind the door. Over here, you decide not to reject the null when you're supposed to reject the null. Does that make sense? So alpha, beta, those are the two errors that we have. In terms of medical terminology, we can sort of extend this. No effect, we could call it as negative, right? Nothing's going on, you're perfectly healthy. So in medical terms, I'll call this a negative. And if you find an effect, then there is something going on. So you're testing positive for something. Good. So I started with the statistical definition. I demonstrated a practical silly case. We still have to determine why Jesse is going to be an awful candidate. And this is the medical way of interpreting. So negative, positive, negative, positive. Good. In reality, or the truth is that you are negative. You perform a test. The test also concludes that you are negative. Naturally, we did not make an error. Good. In reality, you are positive, but the test ends up telling that you are negative. So could I call this as false negative? Or is it a true negative? In truth, you are positive for some disease, some condition, but you perform the test tells you you are negative. Nothing is wrong with you. Is that a true negative or a false negative? False negative. So this would be false negatives. 40 times it was a false negative. Over here, in reality, nothing is wrong with you. You are negative for whatever condition or disease, but the test ends up concluding that you are positive for the disease. So could I call this as false positive? Yes. Now that I've given you false positive, false negative, take a guess as to what this should be. True negative. It's not toilet paper. True positive. Okay. So how do we find this error? So alpha is simply the probability of rejecting the null when the null is true. So naturally, we are making an error. So we rejected the null when the null is actually true. So that is a type 1 error. That would simply be the number of false positives divided by. So you are rejecting the null and you want to determine the total number of false positives you have. So should you divide by the sum of all of these, or should you condition on something? So if you recall conditional probability, if I want to know simply the total number of true negatives for this particular game, this would simply be true negative divided by the total number of trials, correct? So 30% of the time, Jesse is correct in guessing true negative. But here, I'm saying we have to reject the null when the null is true. In other words, you are conditioning on the fact that the null is true. So the total here is actually 30 plus 20. Does that make sense? You are conditioning on this total. So you would write it as FP plus TN. Good. And that would be 30 divided by 30 plus 20, 0.6. 60% error. The next is beta. Where should I write it? I'll write it over here. Can I erase this? Beta is over here, type 2 error. So probability that you are concluding that you should not reject the null, or you end up saying do not reject the null when you should have rejected the null. So over here, the probability, you do not reject the null when the null is actually false. Correct? You should have rejected. In other words, you should be here. But when it is false, we end up saying do not reject the null. So if you have to take a guess, what should the formula for beta be?
Yeah.
So it's Fn divided by
Fn plus 2p.
Fn plus Tp. Good. So in this case, that happens to be 40 divided by 40 plus Tp is 10. That is 0.8 or 80%. Good. So Jesse over here is going to, the probability that Jesse is going to commit a type 1 error in guessing is 60%. Failure again, type probability of type 2 error, 80%. Do you think Jesse is reliable? No. If you go wrong 60% of the time, 80% of the time in two different ways, clearly Jesse is not a good candidate. They're not winning $10 million. Good. It will happen only by chance or good luck or a miracle happening. So, do we understand type 1 and type 2 error? Alpha and beta? Now, there is a related concept. Go ahead. Good. The related concept is specificity and sensitivity. It's used in medicine, biostatistics. Specificity would simply mean 1 minus alpha, how specific you could be. Sensitivity is 1 minus beta. In statistical literature, we call sensitivity to be power. Good. That is the statistical power of a test. So in Jesse's case, 1 minus alpha, 0.4, not specific at all. How powerful is Jesse as a psychic guessing? 20% power. Not good, right? So not powerful at all. So that was our conclusion, that Jesse is not going to win us any money whatsoever. Ideally speaking, if Jesse is a perfect candidate, in other words, I send Jesse off, they're going to come back with $10 million. For that to happen, in our 100 trials that we tried, what should the counts look like? Do you follow my question? What should these counts look like if Jesse is the ideal candidate? In other words, we send her off, we get $10 million. Type 2 has to be 0. Is that good enough? Type 1 has to be 0. and we've got 100, right? It can't be 70-30. That wouldn't make sense. Not an ideal candidate. It can't be 40-60. Not an ideal candidate. For us to be, it can't be 100-0, right? Not an ideal candidate. Here, we want Jesse to walk in, come back with $10 million. So what should these counts be? 50-50. In life, is this possible? If that's the case, we'd all be, flying jets and going to space with a lot of money. It's not going to happen. So there will always be an error here. There would always be an error there. In other words, there will be type 1 error, there will be type 2 error because we are performing a statistical test that is dealing with random processes. So this cannot happen. But the problem here is if one tries to reduce alpha, yes.
So the higher power and the higher specificity for hypothesis test is better.
Best. So if I try to minimize this, I will end up messing up here. If I try to reduce this error, I'll end up increasing that. In other words, we cannot be ideal. It's just not possible. So for a test to be amazing, we need to have high specificity and high sensitivity. In other words, you need to have greater power. So both of them to be ideal, not going to happen. So what we do in statistics is we fix the value of alpha. So I want to reasonably fix the value of alpha and come up with a test that gives us greater power. In other words, you are maximizing power. Good. So can you see? We fix the alpha at some level and come up with a test that gives us greater power. We want to maximize the power. If we could do that, then we have a good statistical test at our disposal. Does that make sense? In software engineering or computer science, we have a binary classifier. In other words, one can classify a 0 as a 0 and 1 as a 1 properly for any scenario. Same concept. A hypothesis test is simply binary classification. And the classifier is amazing if both of them end up being 100%, right? Not going to happen. In medicine biostatistics, when we have a drug or a test, what do we expect? We sort of go for 90% in both cases. That's good enough for us. But if we can come up with a test that is better, great. But we can't minimize both of them. So we fix alpha at a value and try to come up with a test that will maximize the power. Yes.
So when we decrease alpha, we increase beta, don't we? And that would decrease power, wouldn't it?
If we increase alpha, then we would easily reject the null. when you shouldn't be projecting the norm, right? So when this goes up, that probably is going to go down, but it may not necessarily increase the power of the test. Some cases it will, but not necessarily. So there is always a trade-off between these two. We'll go back and forth. But when we perform a test, we want to fix this value and come up with a test that will give us greater power. Yes.
So to get greater power, you have to make alpha bigger, so beta would be smaller.
Yeah, you can keep on making alpha bigger, 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 right? Then you will just simply reject. But that doesn't make any sense if you kept rejecting. Sure, you would keep on increasing this, but still the test is not doing a great job, correct? If you reject all the time. So that would be like a 100-0 case. Does that make any sense?
So then why do you want greater power?
Well, why do I want lower alpha?
To avoid type 1 error.
To avoid type 1 error. So of the two, alpha and beta, in practice, it's called controlling. It is easier to control a false positive, which is why we try to fix alpha. So we always choose a reasonable value for alpha because we can control it and maximize the power. In practice, if I fix that at some level, would I get a test that is 100% powerful? No. In simulation, sure. In practice, not 100%. Not making sense. Yes? No? Why not?
I don't understand why that statement says you want greater power when you obviously want to make alpha as small as possible.
We're not making alpha as small as possible. We are fixing it at some value. I can keep on changing alpha in one way or another. That is not going to give us a good test. You just fix it. What is a reasonable value for alpha if I have to pick? Could I pick alpha to be 30%? Should I? No. That would mean the probability of type 1 error is 30%. Could I come up with an alpha that is extremely small? So 1 in a million, in other words, 0.00001. Is that realistic? No. So what we're trying to do is to derive or come up with a test where you fix this at a reasonable value and achieve greater power. But it's not going to be one, always. Do we remember t-test from 2023? Yes? Do we remember a hypothesis test for proportion from 2023? No, but we do remember the t-test.
I remember the t-test. Yeah.
So the t-test, why do we consider a t-test to be a reasonable test to test for means? Well, one, theoretically, if things just work out nicely. In simulations, if I pick a t-test and I do a simulation, and if I fix this at 0.05, a t-test would give us a good amount of power. In other words, it will give us the correct conclusion when I fix it at some alpha. Of course, I can't fix it at 0. That's ideal, not going to happen. But at some small value. So that is how we say, okay, t-test is a good test for a mean. In this class, we would come up, or we will discuss a binomial test. We will discuss a Wilcoxon test. We will discuss a Kruskal-Wallis test. Why are all these tests acceptable? One, theoretically they work out. Two, when you do a simulation, I know realistically I can't minimize both. So I'll fix that and see if my test is doing a good job over here. And every single test that we will do in this class are good tests because in simulations, things work out. Does that make sense? And theoretically, it will work out also. 2023. If you read a problem or a t-test, and say test at a level of significance 0.05. Do we remember? That level of significance is simply alpha. That is the reason when you did a problem in STAT, a t-test, every single problem that you do will give you a value of alpha. Use alpha as 0.05, or use it as 0.1, or use 0.01. Those are reasonable values. 10% is the maximum we will get for alpha typically. Of course, I can keep on increasing it, but it's not meaningful at all. Are we clear? So the common values for alpha are 0.05, 0.1, and 0.01. Good. The choice of alpha often is subjective, which is why we have another measure, which is p-value. Even that could become subjective. So these days, people have developed other techniques also. Good.